All right. Hash, which means to chop and mix. We have several different areas where we'll make use of hashing. Basic idea is that we'll take a value and then apply some manipulation onto that value. The hash function second. Then take the resulting value to use for other purposes. All right, so some common industry hash algorithms are MD5 and SHA. Grab those. MD5 is just message digest 5. It's just a way of mixing things together. Take a look at that in a second here. And SHA is just a secure hash algorithm. Right, this one's been around for a while. I don't know much about hashing crypto. I mean, they're using, it's called crypto because they're using cryptography, and hashing, one of the areas of hashing is in use for cryptography, usually for the signatures, stuff like that, but we won't get particularly deep in that. The idea of the hash is we take some value and then transform it into, we take some sort of key, typically a key value, and then transform it into a different representation of that same value such that we can have a one-way transformation. Talk about passwords in a second. So scroll down, the real algorithm. Right, so chopping and mixing. So what it does is we'll start just chopping the message into pieces, and then we take those pieces and we then just mix them back together. So down here below the processor, note the binary operations, XOR and or not. You haven't taken the computer math class yet, right? And just means both have to be on for this whole thing to be on. This is an or, that means either the left side or the right side, or both on for the whole thing to be on. And then there's the not operations, such as flipping the bits, and D. So most algorithms will make several passes, and we're going to be doing some scaled down, much simpler versions of things like this, but anding and ORing, exclusive ORing, which means it has to be exactly one on. Just different ways that we can take data, smash it together, and then get a value that's very far away from what it originally started off as. Using MD5 is okay as long as you're not using it for cryptographic purposes. If you're trying to do things like storing passwords as a hash password, which we'll talk about, we wouldn't want to use MD5 because it's not a very strong hash algorithm for the purposes of security. And that's where SHA comes along, and SHA-2 is the common standard, which is encompassing quite a few. And as time goes on, they keep making things a little bit bigger. Let's see these other years when they came out. First published. So, all right, 2015. So I'm sure before too long we'll have even newer versions because computers get stronger. The stronger computers get, the more brute force attacking they can do. All right, so hash functions. All right, so our trivial hash function is called modulo. We'll take the key value and modulo that by another value. All right. Typically, we're going to use this for hash tables. Before we get to that, let's give an example. Say our key, let's say our mod value is 10, and then we'll do various keys. Right, 125 modulo 10 gives us our 5, which keeps the last digit, whatever the last digit is. 17 modulo 10 gives us 7. All right, 45 modulo 10, 5 again. All right, I'm using modulo 10 because the math is extremely easy. All right, so if I have the hash value of 5, it's impossible to know just from this value what the key was. We can certainly eliminate what values it's not, but I don't know if 125 was the key that produces 5 or 45 was the key that produces 5. That's the basic idea of hashing. From the cryptographic side, it is a one-way transformation. So we'll be using mod a lot, especially when we're going into hash tables. In a more interesting area, using hash functions for storing passwords. Right, so it's very bad practice. Bad practice to store passwords. Right, in file, database, wherever. Because if that data store gets corrupted, all of a sudden your customers' accounts are exposed, data breaches are all too common. And if that data breach allows the exposure of that data, it opens your company up to liability and potential loss of money because of that exposure, and a minimum paying the credit bureaus a bunch of money to give all of your members that suffer the data breach a free 1-year credit monitoring program. So the first line of defense when account is created, we'll take the password and hash that key and store it in its hashed form into the database. All right, so login process, or not login, I'm getting myself right. So create account. All right, go create a Facebook account, whatever. And say their name is Billy at bob.com. One of the reasons why most systems like email addresses as usernames because they're nice and unique, and uniqueness is fun to have, right? And their password is Billy Bob. Billy Bob. You don't recover the password. So if where you go to a forgot password. And I've had this, it was a long time ago now, but I went through the forgot password process and they emailed me password. And I was like, whoop, I don't trust this website at all anymore. They went ahead and had the ability to get my password, which means they either didn't hash it or perhaps they just used cryptography and they encrypted it, which by the fact that they emailed it to me, I find very unlikely. Email is not a secure medium, so every machine between their server and my desktop that had access to the email now has access to that password. Probably how that password got breached way back when, because that data tends to live around for a while. People like to mine for things they may find. All right, so we'll get to that process in a second for account recovery. All right, so what we'll do is Billy Bob. And whatever the hash password is, we'll just say some sort of arbitrary value. We'll say that that's the hash password. The hashed password to the database. So when Billy comes back in to log in, they'll provide their username and password. And what we'll go ahead and do is look up user account, the username, and hash password provided to see if that hashed value matches the stored hash value. Assuming we have a decent hash function, then it is extremely unlikely that a different password would produce the same hash value. Okay, so let's go over to files inside the hashing folder. I've got my salty hash zip file. It's going to demonstrate this process. Extract all that. Extracted a time or two on this machine. All right. Where is it? File. Let's see, find the binary there. Okay. Digitally signed, so it's saying I don't want to run it. Where is it? There you are. Okay. All right. So for example, register an account, username, whatever, password, register the account. All right, and this is the value that we store in our database. So this table or grid down here represents our database. So if I want to log in, go through the same process, and it says the login was successful because they looked up the username, looked up the password. If I change one little bit, all right, say like I add a 1 on here, try to log in, it's gonna tell me the login failed. If I create another account, right, just adding that one value, corresponding hash password is very, very different. If I instead just change a single bit, and there's only a 1-bit difference between an uppercase and a lowercase character. All right, so here's the capital G Glenn versus the lowercase g, right? Very, very, very different values, and that's even just changing a single bit. All right, problem. So here's the problem with MD5. If I take that hash value and I just search for that, and you can see that it tells me that the value was Cuevas, and here's the little passwords text file. on the internet. So MD5 is not, as mentioned before, it's not secure. And the steps we've taken thus far have not done much at all to protect this password. And the big problem here we have with this one is that the password's too simple. We'll get to that in a second. But the way that you can break hash passwords is by doing a reverse lookup. And the way you do the reverse lookup is you just go ahead and take all the common passwords. Right, so let me go back to my app. Let's change my password to something clever, right? 1, 2, 3, 4, 5, 6, right? A clever password. Right, take that, search for it, right? And we will get 1, 2, 3, 4, 5, 6. It's not a good password. There are many passwords that are not good passwords. So let's do this @1. People like to do simple. We'll see. This might be good enough. But we'll find out in a second here. If the internet has the answer, right? See, that password is not a good password. So if we do have a good password, let's say, all right, today is Monday, not my favorite day of the week. Right? Smiley face, something like that. There's good, that one, and we'll see what kind of reverse lookup we get here. All right, 0 hits. This is why having a good password is important, because you can't trust every place that you create an account on is going to have strong security in the way that they're storing your data. And if you share passwords, right, so on PlayStation Network, and you use the same password for your bank account, your credit cards, and your PlayStation Network, which was breached. It's been a number of years now, maybe 5 years ago, I guess. They had like 2 breaches in the same calendar year. It was ridiculous. Right, and usually it was right there. Your username was your email. All right, same as your email. They got your email. They got your password. Bam! They just start searching. Yeah, do you have an account on Bank of America? Let's go see. Use your email and that same password. Oh, you do. That's a good. And well, you don't. All right, we'll try that. All the big banks everywhere that they can pretend to be you and get your money to leave your accounts. All right, so secure passwords are quite important, because while we can try to take all the common passwords, names, addresses, phone numbers, everything that's in the dictionary, words that are commonly spliced together, right? You just basically take all those words and then hash each and every one of them. And then you just build that lookup table. And it's very easy to find a value in your lookup table and then see what value was that produced that hash value. Right, so that reverse lookup is easy to do. Trying to mathematically unwind this value, that is still hard, even though it's just using MD5. And so that's where a good password is going to help you. Now, you can't, from the application side, you can't trust your users to have good passwords. So first level here is an improvement. So if they're using medium to strong passwords, if there's a data breach, then it's very unlikely that account will be breached, and we'll have enough time to say, okay, there was a data breach. All of your passwords have been reset. Basically, set a flag in the database that you try to log in. You're going to have to create a new password. They're going to email you a code so you can authenticate that you're the person changing the password, all that good stuff, similar to what you use when you registered. And so that's the first, that's like minimal security. Like anything below this there's basically no security. I just finished watching Mr. Robot. That was an interesting show. I got a coworker. He's a white hat. So he went to one of the I forget those cons are that he goes to, but they actually had the main actor of the show at the one of those, and yeah, what they're doing is legitimate kind of hacking going on there. All right, so next level of security is a salty hash. When a user creates an account, we'll assign that user some random value, and we'll use that random value in tandem with the password. Essentially adding security to the password. So even if the password is password, if I can type, the reverse lookup, and even keyboard, my keys are just too worn out. The reverse lookup will likely fail. Right, so here we'll go ahead and go back to simple password. Password is my password. And we'll just create our accounts like this. We'll see that my password is the best password of all time. All right, we get results. So here, generate salt. So this is a cryptographically random value that I'm just appending or prepending. I forget. We'll show you the code later. It's in C#. So you don't need to worry about the code. It's just for demonstration purposes. But now I try to search for my password, right? Again, no hits. So even though the user did not use a secure password, we are a little bit better protected from a data breach, because now the data breach has to take, let's say we didn't even do a good job protecting the salt. They've got the salt and they've got the hash. All right, so now they'd have to know what the code was. If we're doing something similar like prepending or appending, then we're going to buy a little bit of time, but then they still have to go through that database. It's not double hashing. We'll talk. Double hashing is a collision resolution strategy that we'll talk about later. All right, so they still have to, right? They can't just do the reverse lookup, right? So they actually have to do work on the data. So they're going to have to take the data, take common passwords, and then take those common passwords, and then take the salt, and then blend that salt in with the common passwords, and then try to figure out if it matches anything in the database. So that in that level, we're only going to be compromising people who have poorly selected passwords, right? Because we see people had strongly selected. That's just even adding the salt is just an extra layer of security. That's the nature of security. Security is all any secure system does is buy time for there to be reaction and detection of the attempt to breach the system. And so it just depends on how good the security system has and how well monitored that system is, right? Just like a bank. If they got a flimsy plastic door as a vault door, it's not going to take you long. You can get in and out before you get caught breaking into the bank. But you had an extra 4 inches of steel onto that door. Now it takes a little bit more time to get through, right? And the complexity of the lock, which reminds me, there's a YouTube channel called Lock Picking Lawyer. It's kind of crazy how weak most little locks are to breaching from basic tools. Anyways, same idea. The more expensive, the more complex, the more advanced the lock, the longer it takes, and the increased likelihood of detection. But if it's a weak system, the weak system is likely to get their vulnerabilities exposed, and problems ensue because of that. So just adding salt to the simple password now makes that password a lot more secure, because the hacker is going to have little to do with this particular password that's in the database are going to have to do a brute force attack on the entire, wherever that text file we saw over there was. I don't know how many millions of common passwords have been aggregated over time, because every time there's a data breach, right, that password list just keeps growing. Right. So whenever if you get an email saying there's been a data breach in your account, that password is dead to you. Don't ever use that password again, because that's now probably in a text file out there somewhere, and someone's going to try to use that. So some systems will even prevent you that, because hash history for your previous passwords, just the hashed value. And you try using all, and they're like, nope, sorry. Right. So the systems have those rules to better protect you and themselves, because if their system gets breached, they're the ones liable for their breach, but it's your information that they're also still trying to protect on the other side. So it's annoying. My favorite one was like American Express for like longest time was like, you had like had to be exactly between 5 and 8 characters and have special characters. So it was like my password's like 15 characters long. How am I supposed to make a good password out of when I'm constrained by so much? Anyways, longer, the more non-wordy it is, or even this randomly generated salt would work well. Go back to the code. I think it's in here. What's my CS associated with C#? Okay. As long as that can take it too long to load up. Should have got the good old Notepad++. Okay. And even this sample application, it's using MD5, which is not. Right. So all this other code here, that's just the form code, data logic, nothing special. Hashing wise, all the interesting hash code is inside this little hash code section. All right, .NET has a cryptography library. It's probably kind of small, like a little bigger. Well, that is just going to give me some good random number generation, and I convert it to a base 64 string so we can actually kind of see what it looks like. And then password hash, right? All I'm doing here is just concatenating password that was provided and the salt, and then we're just computing in MD5. MD5 hash is also just one of the other cryptography libraries, right? So even for this purpose, MD5 is okay, but you shouldn't use it. You should be using SHA. When I created this, I don't know, 10, 15 years ago, something like that, MD5 was a little bit better than it was, or at least I wasn't aware that MD5 wasn't as good a player in the field at the time. Right, probably a SHA. I don't know what it's called. Right, there's SHA, lots of SHA options. We would want to be using these instead, but this is just a demonstration, not a production level code that you want to rip out and start ruling the world with it. SHA is just better. I think it has more bits, and has a better algorithm. Right, the number of possible, I think the number of possible hash values that it can produce is just larger. And the larger the number of values, the more, right? I'm sure it suffers still from, well, here, might as well do it. I'm curious. Let's see if we can go ahead and find it. How it still is, even if we are using SHA. I don't think it's going to help with the reverse dictionary attack. I think the reverse dictionary attack is still going to cause problems, but might as well just go add a button. Let's go salty style, or SHA style, that is. SHA. All right, button 1. Good old copy paste. always the wrong way to write code, but when you're trying to go quickly, create hash password. Go ahead and generate method. And then we'll go steal this code. Ooh, I stole the wrong code. Text. All right, hold on. Create password hash. Let's get all my extra stuff out of the way. I think I did it. All right, hold on. Forget about side by side. We are now going to be just changing what we did to SHA. All right. MD5. And we'll see what's available. Okay. Need some data, hash name. Yeah, there's one there. And why are you mad at me? Template managed. What are you bringing back here? SHA 256. Okay. Compute the hash, compute the hash. That might be good enough. We'll see if I broke it or not. Writing code on the fly when you got 40 people watching you is always a little bit tricky. Of course, should have 20 more people watching. And we'll get to that later. Could not. Programs running. Yeah. All right, let's find out how. Good, right? So this value, see, that's longer than what it was before. Now we get to check. All right, so that's how long it was before. What you want to duplicate? All right, longer by twice. SHA 256 tracker, right? So we got a hit. So didn't get nearly as many hits as we did before, but I imagine if we change to a simpler password, we're probably get more hits. All right, 6,000, 8,000. All right, so SHA definitely better because it's more data. Right? Their dictionaries, yeah, it's literally be twice as large if they had a 3 GB dictionary. For the reverse lookup, now they have to have a 6 GB because just the raw data is that much bigger. And of course, stored as a base64 encoding. Just pretty common encoding format, and this type of base conversion is actually one of our other hash functions that we can use. So salty hash would then be the next level still, right? get our salt. Now we got salty. And now our data is not going to be popping up, all right? Because the number of, right? This is a 64-bit, base 64-bit encoding. That means there's 64 possible values each character here can have. And that's what? Let's see how long that hash value is. That hash value is 66, white space there, 64 long. All right, so bust the calculator out. 64 to the power of 64. All right, 115 digits, 116 digits, 3.9 power 115. That's quite a large number. Quite a large number. Right, so now that's, I mean, phishing. I had to report a phishing email today, Coinbase, with a little tilde over the E, saying, oh, your right? Crypto attacks are the most common attacks these days, it seems like, because more and more people are getting wallets or exchange accounts. And basically impossible to hack someone's account without having data or basically getting onto their computer, right? Slave their computer and find the token on their machine, because that key is, it's like, it's something like, I don't have word wrap on, so that messed up my little demo there. Let's try that again. All right, the key is something like that big. So it's pretty much ridiculously impossible to hack the key. So what you have to do is you have to hack the middlemen, because the middlemen have the keys. So you hack where the key is being stored so you can steal the keys, right? So it's like attacking a bank. If you steal the password, the 4 inches of steel, or the vault code, the 4 inches of steel is irrelevant, right? Because you have the code. So it's the same idea going on there. I read about a recent one this week or last week. A bridge was attacked because it required just 6 of like 12 machines to authenticate the transaction. And the attackers they breached 6 of those machines and just approved all the transactions. So they didn't even get anybody's keys. They just did effectively a man in the middle sort of attack, where they breached the infrastructure in the middle and just got everyone's wallet, had enough wallet information, and wallets were hot, to allow transactions to happen. And then all this stuff. Crypto is still not an area that I have a lot of technical knowledge on yet. I'm learning bits and pieces here and there, but it is a little bit of the Wild West out there. It's unregulated. There's someone steals your crypto money. It's like, okay, who you go to? It's because the person who stole it probably not even in the same country, right? So your local authorities, and you can go to local police station and say that they stole my money in my crypto account. They're like, okay, they'll of course have you fill out a form and all that good stuff, and you need enough people in aggregate to report the same type of breach, and then it goes up to the FBI and working with Interpol. Who knows? Just gotta be very careful. Make sure you're using a reliable company and they have appropriate policies in place for all that good stuff if you're going to venture out into there, which I'm sure many of you already have, and that numbers only seems to be increasing. And of course, make sure your password's secure, and if you have your own wallet, that key is secure, because that key is like your password. Very, very, very complex password, but it serves the same purpose. Yes, two-factor authentication is super, super important. Hopefully what the breach wasn't you losing your phone, and your phone being your two-factor authentication with all that good stuff on it. So yeah, it had to be two-factor authentication, definitely helpful against external attacks. But if it's a direct attack where they, they steal like stealing your wallet, stealing your phone, which is often your wallet. This is why having a good passcode on your phone is also important. Because if they can't get into the phone, then they can't get all the many important things that might be living on your phone. Because two-factor authentication is very important. If that system offers it, I highly recommend you set that up. Because you never know when that system is going to be attacked. Right. All right. So all that's about, all that hashing is all about a hash function that's just going to take data that we want to protect and transform it in a way that we can't mathematically reverse it. There are other ways we can attack it, as we see, but mathematically the information is protected and at least long enough, hopefully long enough, that the breach is detected, announced, people's accounts are locked, so that no unauthorized actions can happen, and then so on. All right, so modulo, one of the other places that we'll use these hash functions is with data storage. And we can build a quick lookup system by making use of hash functions. Functions to drive how we store the data. All right. This data storage might be called table or dictionary. The idea is that we can very quickly go one if things are working properly, find where the data is in the corresponding table. And that table is going to be array based. Going to be array based. And we'll expand on that array based nature later. But the idea here is, example, we'll have a table with 7 elements and use the modulo function for the hash. That hash value is then used as an index into the table. All right, so building the hash table. Hash key takes us to index, and then write the data there. Okay, so for keys. Keys modulo. So our first key is 10, apply the modulo of that, gives us a 3. And we'll go ahead and go straight to the table, index into the array, right? Arrays of random access. Indexing, it takes the same amount of time to get to any position in the array. 20 takes us to 6. Okay, 20 divided by 7 goes in twice, the remainder of 6. All right, modulo. Let's see, 30 takes us to 2. All right, so one of the key things to note about our data in here is that there is no order, right? Note that we're not storing the data in order. Data lands where the data lands. The lookup, right? Same process. Hash the key. Go into the table at that index and pull the data back if there is a key match. So if I do a lookup on 30, it takes me to index 2, and at index 2, we have 30, right? This is a simplified version. This is also what's known as a hash map, where we just have a bunch of just keys that are in the data set, but no actual corresponding values. Usually a hash table, there's going to be a key value relationship. So for that key, say this is like your user ID in the database or something like that, or your username, then the corresponding data, right? Your password, your salt, last time you logged in, first name, address, whatever it is, this particular system has information about you on that corresponding data, then loaded in the record object reference to wherever that object actually is. But as long as the key is there, we're matching, we're good to go. Do a lookup for, say, 50, takes us to index 1. Index 1, we have nothing. So that key is not present. And this is the simple case. The third area, signing. We can use a hash function to sign a bit of data so that when the data is transmitted, that data can be hashed and then checked against hash value to validate integrity of the data. Right, this is way more common in the earlier days of the internet, because the network reliability was quite poor. Right, so you download a large file, say 200 kilobytes, because in the early days of the internet, that was a large file. Yeah, good old 14.4 KB modem. You're looking at still that's 15 seconds. Yeah, 15 seconds to download that GIF your friend emailed you. Right, so hash value gets downloaded also. And at the receiving side, hash the file. Right, the 200 kilobyte file, 200 kilobyte file. And if we get same value, then we're confident that the data is correct. This particular pattern isn't seen too often. Sometimes I'll see it. Websites still, when you're down something large, they give you that signing. Part of that signing also helps for authentication purposes, and usually that's signed with a different type of signing pattern, but same premise, so that you can know that the code or the binary, an application that you download is authentic and hasn't been altered by someone staging fake sites or they hacked into, like, let's see, it was SolarWinds. They had a hack last year or 2 years ago where some sort of Russian entity figured out the password to their content delivery network was like SolarWinds 1 or something like that. It was a simple password, right? And so they did basically a brute force attack on just simple guessing and then common patterns on simple guessing. And they went in and they replaced binaries. So when companies downloaded the binaries, they infected themselves because the security in the middle wasn't good because they didn't actually sign, right? Digital content signing, they didn't sign their data. So applications like, yeah, that's got the right name on it, whatever it was, and we'll go ahead and use it. So they're probably going to be dealing with that kind of repercussions for a little while to go here, especially since a lot of companies use mine included SolarWinds products. Let's see. All right, so those are the 3 areas that we're going to be digging in deeper. Most of what we're going to be doing is hash tables. Cryptography, mostly we've covered what we're doing here. If you have more questions on the cryptography stuff, because that's probably the most interesting area of this entire section, not the entire class. I thought salty hashing, when I first read about it 15 or so years ago, is a very, very practical use of hashing. A more common use is going to be dictionaries, because looking things up quickly is very, very important. So let's get into more of that. Hash functions. All right, so hash function is pretty much core to hashing whichever way we're using it. A hash function is going to be involved, right? The key difference between a hash function and we're digging into now with our hash tables is just what we're using the function for, how we're using the result of that data, right? With our passwords, we're just using it for data storage and then data comparisons for, validation process. And the signing was very similar to the passwords, but for a different purpose, just to make sure that the data is maintaining integrity with what we're working on. So our various hash functions that we'll look at. Hash functions, again, this is going to be the one-way cryptography. We're going to look at modulo. Then we have folding, which we have 2 subcategories of boundary and shift. Then we have double hashing, radix transformation. Brain's telling me I'm forgetting about something, but go back to that later. Okay. All right, modulo. Just taking the key, possibly first transforming it to a number, and then dividing it by number and keeping the remainder. All right, so like we had before, if the number is 25, my keys, right, 100 just goes to 0, 25 goes to 0, all right, 4 goes to 4. Nothing terribly exciting there. The data is non-numeric. Then we need to first transform that data. All right, so a simple approach at transforming data. That is, we'll just use ASCII, same difference if it's Unicode. Nature is to use a fold. All right, so let me get my link. Let's see, do we have, yeah, there's folding, mid squares. I knew I wasn't forgetting somebody. Folding, folding, folding. Right, and a few different ways of doing this. We have boundary folding. Let's see if we can find where this is. I think, yeah, I have to go. Wikipedia doesn't have everything, so I'll have to find the links for you in a minute. Should have that elsewhere, so just grab that. Because I do like to forget which is which, but we'll fold the data. Character by character. First extracting underlying integer value. All right, so for example, if we want to transform, say our key is ABC. Right, the ASCII value of that is 97, 98, 99. Folding that, we'll add 97, 8, 99 together. And that's easy enough. Should be right. 270 plus 24 should be 296. I don't trust myself. It's 98 times 3. 98 times 3, 294. Okay. I say one thing, type another. All right, so 294 is our hash value. All right, programmatically, this is pretty easy to do. All right, for example, all right, static int fold, take a string. All right, int result equals 0. Just look at each letter in the word. Add back to the result whatever the value of that letter was, and send the result back. All right, so if we want to go ahead and fold ABC. All right, spit that out to the console, right? 294, just like we had on our white. All right, let's go ahead and change 1 bit in our data. Run it again. All right, the corresponding hash value. Even with its simple hash function, still we get a little bit difference. It's not a very good hash function. I'll have to just rearrange. Right, rearrange the letters, same 3 letters, and the order doesn't much matter at all for this fold. So that causes us to get multiple hash values. And we get multiple hash values for different keys. That's going to cause a performance degradation of their hash tables, which we'll see shortly. Again, this type of folding, it's super simplistic. Right? When we looked at MD5, it's doing a lot more folding, but folding the data, right? Chop and mix data folding is a common mechanism that the industry standard hash functions are going to be using. We're just paring it down to very, very simple way of doing things. Let's see, the radix transformation. All right, and we'll get deeper on these as well later. Radix transformation, right, changing base of the data from one base to another, right? Such as going to base 64. All right, ABC. I don't want to decode, I want to encode. All right, where is it? There we are. Okay. ABC. All right, and base 64. That becomes that. So copy that data. All right, so ASCII or Unicode, I don't know what the website's using, to base 64. ABC becomes that. Let's go capital ABC. Encode. You see most of this is going to look the same because it's just doing a character by character encoding, right? So a lot of this is looking the same. Right, if you're not familiar with base 64, it's very simple, just A to Z, 0 to 9, and right, that gives you 62 of, right, 26 plus times 2, 52 plus 10, 62 of the 64 characters that you can use for base 64 encoding. Then there's, I think, slash and equals, if I recall correctly, are the last two bits. Let me make sure. Okay, 64 characters. Those two plus, plus and slash. I was getting my cryptographies mixed up. Plus and slash. All right, and these characters are quite good at encoding binary data. So if you're dealing with binary data, you very often see it encoded this way because binary data is a quite a pain in the butt to deal with in a binary fashion. All right, encode, same idea. Like we had before with our values here. And here our base 64 encoding is working a fair bit better than our other folding was. Right, all the values that came back were different. So changing the order, right, same characters, different order, gave us a different value. And then of course, this still needs to be normalized down into the table. I will give you some links for some reading on the other hash functions to do. But let's start getting this into a table. Whatever the hash function is, it doesn't matter too much. It just matters that we're using a good one, preferably, before we start dumping things into the table. All right, so using the given. Yeah, we'd only hash the keys. Using the given hash function, we'll hash a key, then normalize hash value by applying modo table size to get index of where we want to drop the data. All right, so key hash function x, just call hash x, result. All right, so whatever the hash result is, don't much care. What the function is, all that matters is that it goes somewhere into the table. All right, so table size, we'll just say it's 15, some arbitrary value. 15, let's go this way. Same difference, we've got our index, and we have our data. All right, so our key value is 100. Data is whatever the associated data is with it. Don't much care. It could be a book, a car, an address, a user in the system, whatever it is. And we just drop it in. Yeah, you know, make my data smaller because my table cells are kind of small. All right. All right, 10 ended up being in 12 because of whatever the hash function we used. 20 goes to 7. 30 goes to 5, and 40 went to 2. Right, more or less arbitrary values. Right, the lookup, same process. Take the key, apply the hash, then normalize the hash value, and look up at that index. The key matches, the value there, and we have a hit. Right, common place, one of the common places that we're going to use this, if you have a website, someone is visiting your website, typically you're going to be tracking some state on that user, whether they're logged in or not. They're going to have a session ID that tracks they've been to a page, if they've seen page 1, page 2, whatever. They're more or less a unique visitor to your site. And you might be tracking information about their visit, right? How long have they been here? How many clicks have they been sending to us? How many ads have they seen? How much revenue are we getting from this user? What can we get this user to create an account? Have they seen this particular pop-up or been enticed to do action A or B, whatever it is that helps generate revenue for a particular website. So as a person's working through a website, they might be on a page for a matter of seconds and they go to the next page, and then they go request that page, or they do a get request against the website. Website's going to see what resource or resources do they want. Is this user already logged in, or a user that we have a session on? If they are, we're going to look at what session state is relevant. Right, they may have selected a theme. They're like, right, they're on GitHub and they're like, they wanted the dark theme, so they click the dark theme button. Right, the user shouldn't have to click the dark theme button every time they go to another page in the site. We want to remember that information. And that information, it might just be stored locally on the person's machine, but we might be storing the information on the server for what style sheets we send back, all that good stuff, whatever the information is. As soon as a request comes into us, we want to find that information quickly. So we're going to have that session state stored in a hash table or dictionary along those lines. So we take that session ID, normalize it to the table, and then try to very, very quickly look up that information. All right, so when we start to fill up a hash table, there is going to be an increasing chance of there being a collision. A collision is when you have two different keys, both having the same location in the table that they are trying to resolve to. All right, so let's take key hash value and then normalized. All right, so there a key is 10 as before, hash value is some different. And keep things simple, table size is 10. So normalize, that's gonna go to index 3, key 20, hash value 321, normalize it goes to 1. Hash value 456 goes to 6. Oops. 40 goes to 493, and we get our first collision. All right.
Professor.
Yep.
If there are two keys the same, can they share that index?
They would no.
No?
Oh, well, not intrinsically. You can, of
What do you mean
course,
by that?
the default state is they know a cell has room for one occupant, but we could, of course, expand the cell to be capable of storing more. So the answer is going to be yes and no. For now, it's no, until we come up with a different approach to store more than that, which we will get to when we get to chaining.
Okay, thank you.
All right, so our first key, 10, went to 3. All right, first entry, there was a 0% probability of collision because the table was completely empty. Now that we have one value in the table, we have a 10% probability of collision. 1 out of 10, given a random value. There's a random chance of landing on already occupied cell. 20 did not, in my forced data, happen in that situation, but now we're getting to the point we now have a 20% chance of there being a collision for the next value that gets added to. All right, 30 went to index 6. We didn't have a collision. 140 lands. All right, 40 is trying to land at index 3, but that location is occupied, and thus we have a collision. And this collision needs to be resolved. And the presence of a collision is going to cause our operational efficiency to move away from constant time. All right, so let's go ahead and take a 5-minute break, and then we'll move on to how to start resolving collisions. Okay, collision resolution. Collision resolution is designed to handle what to do with data and attempting to add at an already occupied location, or the reverse, doing a lookup, and the lookup address does not have a matching key. Open addressing is, there's a couple of variants. Basically, just start walking down the table from the collision point, looking for an available location. The first version of which is called linear probing. One by one, look at the next element, the table. If it is unoccupied, drop the value there. Note that we'll be treating the array as though it is circular. Circular, meaning if the next value is going beyond the end of the array, we'll loop right back around to the beginning, just like we did with array-based queues. Let me go get the data that we had here. All right, so 40 tries to go to 3. But we had a collision there. 1 over is available, so we'll go ahead and drop the data in. Start adding in more data. 50 hashes to the value, whatever, 912. 912. That gives us the index 2. 50 fits in just fine. Come on with 60 and 60 hashes to 141. We get another collision. All right, so 20 is already occupying position 1. So we'll try position 2. It's occupied. 3 is occupied. 40 is occupied. And 50. Found a place to put it. All right, at this point, we have a 60% probability of the next data point having a collision if it's random data instead of forced data. And the way our data is at the moment, we have a single cluster. Drawback of linear probing. That can lead to primary clustering. The values being held in the table are clumped together. This leads to performance degradation. All right. Yes, we just keep going. If we had, let's get our circular part there, 70 goes to 399, normalized index 9, fill it up. And 80 goes to 409. Also trying to go index 9 and restart at 9, wrap around. And we filled the first spot. All right, table's getting pretty full. All right, so let's see. Did everyone have a unique? How many use the same value? Right. So everyone had a unique hash value, which was good. So our hash function was working very well, but the fact that we had to force it to fit into a table, right, that caused it to run into problems. With this small of a table we have here, odds are going to be quite good that we're going to hit a collision. Quadratic probing. It's going to be similar to linear. Instead of just offsetting by 1, we'll go by 1, 4, 9, 16, etc. away from the collision point. Trying to find an alternative location. All right, so go ahead and use the same data. Yeah, we're just gonna do it. We're just gonna cause collision mania here. Okay, hash value is 117 or 10,017, whatever it is. And we're gonna use our good old easy math table size. It goes to position 7. Let's see. All right, so 10 goes to 7, no problem. Unoccupied, but 20 is going to come along and give us a collision. 1 away is still the same as before. Not too far away, it's still close to it, but it's a collision. Collisions are bad. It can cause performance to fall down. All right, so again, collision, we try 1 away. 1 away is occupied, so now we'll go ahead and do 4 away from where we started. So that's 1, 2, 3, 4, also known as 11. And we'll drop the value in there. We had our collision, but we've got resolved and we kept some space. Right? The idea being to reduce our clusters a little bit. Let's see, I can go 1 more here. 5, 4, 1, 7 takes us to 7. All right, so first time collision, resolve collision, 1's occupied, 2, 3, 4 is occupied, and then 9 away, also known as 1 less, is going to bring us over here. A little bit of a cluster forming. If 50 comes along and wants to go to index 8, we have a collision. And this particular collision chain is unique from our other one because it doesn't have the same hashed index. We still have a collision going 1 away. And we have a collision. If we have more collisions, it's 8, then we're going to go 4 away. And 60 is going to 88. Just go to 8. Collide at 8. Collide at 9. Go 4 away. 1, 2, 3, 4. And we're still keeping some spaces here. So quadratic probing does help lessen primary clustering, but at the cost of adding secondary clustering. All right, keep having values that want to try to land within a range of the table. They are going to follow different patterns, but this cluster, if we have the same pattern here, let's compare. In fact, let's compare. So comparing to linear probe. same data. Yeah, having space means there's opportunities to get through a little bit easier. Because if we can find a space, then we don't have to go as far away from our ideal location. Okay, so let's reset the data. All right, 10, 7, linear probe for 20, linear probe for 30, linear probe for 40. And then 50 comes along, linear probe, 60 comes along after that, linear probe. And 60 is quite far away. So let's compare the lookups. Comparing the lookups of quadratic versus linear. So our key, we've got our quadratic, we've got our linear. Good enough. 10, 20, 30. If I can type everything fine. All right, so 10. All right, that's our first value. So they both required just to look up to the original location, no collision resolution. 20 for quadratic was 1 away. So we had 2 values that we looked at. Same thing with linear for 20. 30 quadratic. 30 looks at 10, 20, 30. 3. And it's going to be the same thing over here because I didn't mix my values very much. Still 3. 40. All right, 4 giving us 4 and 4, same case for both of them. Now here with our secondary location. All right, 50. 50 went to 8. It was not a match. We went 1 away. So we looked at 2. Linear. Looked at 1. We started at 20. 1, 2, 3, 4 values. 60. 60 collided 8. Looked at 20. Looked at 50. We found it over here at 60. So we had 3 away. Linear, 1, 2, 3, 4, 5 values that we had to look at. All right, so the quadratic probing things still got quite bad, but we had 4 things go to the same location. That's 4 things with the same location. That's just going to be what it's going to be. But by skipping along and keeping our holes available in our availability spread apart in the table, a little bit more distributed, our quadratic probing had better overall lookup time. All right, another way we can do this is with double hashing. Let's see. Italic. All right, so let's open addressing type pattern. So double hashing here. We'll try to take what quadratic is doing one step further by using a different hash function than the initial hash function. Hash function to determine the initial offset of where to try to resolve the collision. Try to resolve the collision. After which we can then fall back to linear or quadratic probing. Right, so the idea is two keys landing to the same place, or multiple keys, not constrain ourselves to two, landing to the same index in the table, all following same progression. That point leads to degradation. So instead, we'll somewhat be random with where we navigate from the collision point. Okay, so key, hash value 1, and we're going to fold in a second hash function. So we'll have hash value 2 if necessary. And the index, let me swap the word here, where we're trying to go. This should be a table. Let's just make this table. And we'll get things colliding. As usual, we'll use table size 10, keep our math simple. All right, and whatever the hash values are, we're just having rotten luck, and everyone wants to go to the same location in the table, right? So they're all trying to go to index 3. Now we don't need a hash value 2. For the very first insertion, because there's no collision to resolve. But for the next one, hash value 2 might be, I'll keep these small because we're going to be using them as an offset 5. So we're still always, when we're doing collision resolution, we're starting at the collision point. So if we're doing linear probing, moving away, or quadratic probing, or whatever we're doing that at the collision point. And we're going to offset from the point. So 5 away from 3 is at 8, and 20 drops over here for our collision. The hash value for 30 with the second hash function, since it's a different hash function, the hash value is likely going to be very different as well from the first, even though we had unique hash values with our data set, right? Forced, of course. Having a second one, the probability of the collisioning following the same path, or a chain following the same path, is going to be reduced. Right, so 30 ends up over here. And we'll go ahead and have this be, what, 7. It's good enough. Yes, yes, yes. And that takes us over here to 40. Still entirely possible things won't go as we want them to go. Might have someone, oh, the number might be so large. Let's just say it's 10. Right? 50 wants to go to index 3. Okay, we jump to a different location in the tail. We jumped, actually having to jump back to where we were. And then we fall down to a simpler probing mechanism at that point. And so my secondary location didn't work out. So we should go ahead and from that secondary location, just start rolling out. And let me do another scenario. We'll have this one also go to 7. It's collision, and 60 ends up over here. All right, as the table keeps getting fuller, probability is just going to increase that we're going to have a collision. Does double hashing sort of makes sense? Questions about any of these 3 hash functions? They're very related in how they're addressing problems. Yes, well, when we first create the table, it is going to be fixed size. If we need to resize the table, which we'll get to later, that is going to require much more effort than it would be just to resize a regular old array, because the table size is important to the normalization process, the modulo operation that we're going to do. And if we were just to change the size of the table, then our road, it's like changing the signs on the street. So all of a sudden, no, things are not going to work out the way they did before. Heavily addressing. All right. We have a couple of patterns that may look familiar. Familiar chaining. Chaining uses an array of linked lists or buckets, which is a matrix for storing the values. All right, so first up, we'll have chaining. As I mentioned before, it will be an array of linked lists. If there is a collision, then we'll add value to that particular list. Unless other circumstances apply, maintain the list as sorted, as that will allow an early exit. Early exit opportunity on the lookup. And the reason why I say that, the idea of hash tables is we're building the table and we're doing frequent lookup. The key operation that we're expecting to be done on the data set that we're working with is we're going to be looking up data often. Right, so going back to the website scenario, right? Visitors, right? Whatever website is or server, it doesn't have to be a website. Servers, client-based server communication. You're playing a game and you're sending traffic to the game server, and they need to look up your information quickly and make sure that you're not hacking the packets before you send it to them to say you are somewhere else than you should be. So you log in once, your data is looked up often. But the number of times we look up your data on the server relative to the number of times you log in for any window of time is going to be astronomically higher. So the operation that we're optimizing on is on the lookup. So that means anything that we can do to improve lookup time is something that we're going to do. All right, so let's see. This data is good. Steal that data. It's not that good. Let me make the numbers a little bit smaller. 1, 2, 1, 3, 2, 1. And I guess I have to change my hash values a little bit. 1, 2, 1, 3, etc., etc. And we're probably going to be dealing with a smaller table size here when we're dealing with lists. So as we had before when we had our adjacency list, or still have our adjacency list since we haven't had the test on that yet. We will build out an array at the top level. And then from there, we will build our lists as needed. That's a screenshot of the data. And we can work. Right, so it's just list 0, 1, etc., etc. Indexes into the array of our linked lists. And our first data point comes along. 10 goes into our list. There's no one else in that list, so we just add the node to that list. Right, 20 comes along. Goes into our next list. Right, no collision just yet, so everything's landing just fine. 30 makes the visit. That generates a collision. And we add it to the same list as 10 was added to. 40 goes to list 3. All right, so one of the nice things about chaining is keys that end up going to different indexes aren't going to be stepping on each other's toes. All right, 50 went to list 2. Same old as before. It gets added to the list in sorted order. The data that I added here happen to all be added in ascending order, so it looks like we're not doing anything, but we'll do another example with data coming in a different order. But looks very much like an adjacency list. Right, in the order in which the data arrives. If we weren't maintaining order, would end up with the data in a different pattern. I mean, that one doesn't much matter. Just go ahead and move 60 up. And we can go through the various states. Okay. So build the table again. Building in a different order is not going to matter because we're going to be maintaining the data in the same fashion. We'll strip it down. Start over. Right, so 60 comes along first. Create the node, add it to the list. 50 comes along, goes to list 2. All right, that's our initial state. Now we're going to have our first collision. Go ahead and get this set aside. 10 comes along. I think I misspoke earlier. 10 comes along, comes in 1. All right, and what we're going to want to do is insert that. So that is in order. So our lookup is going to be at the same time, right? So if we're doing a lookup for 5, say 5 goes to list 1. The first value that we look at is a 10. Well, if this data is unordered, we are forced to exhaust the entire list before we know that 5 is not here. This person is not logged in, redirect them to the login page. If this is ordered, as soon as we get to this first element and we can see that the value is greater than what we're looking for, then we can stop digging through this list. So when 20 comes along, right, we'll do the same thing. 20 wants to go to list 2. List 2 already has a value. So when we insert the node, right, it's inserted in front of our existing nodes. So we can keep our data ordered. All right, 30 comes along, goes to list 1. All right, so a new node is created and inserted in the middle. And then lastly, 40 can jump into that last position there. All right, the ensuing table is same as before. 10, 30, 60, 20, 50, 40, 10, 30, 60, 20, 50, and 40. So it does not matter the order in which the data is presented. All that matters is the hash value. We'll have the same matrix in the end. Bucketing. Bucketing. Here, instead of just using a single dimensional array, we'll use a matrix where the bucket size will determine how big each bucket is. Which drives number of columns, rows, depending on how you depict it. And this time I will do this. All right, so smallest we can have is bucket size of 2, otherwise it'd just be a regular hash table. And it's bucket size 2, table size 5. So we have our index. And I'm missing a column here. And then position 0, 1, and then 0, 1, 2, 3, 4. All right, so what we're going to do is fill the buckets, keeping each bucket sorted. If a bucket overflows, it leaks into the bucket below it. Key, and then whatever its hash value is, doesn't much matter at this point, whatever index it's going to. All right, so the key is 79, and the index it wants to go to is 0. All right, drop it in like before, no problem. If 15 comes along, let's go next 1. All right, no collision, no problem, drop it in. If 25 comes along, let's go to index 0. All right, 79 moves to the side, make room for it. Everything's good to go. 41 comes along, bucket 1. Go to bucket 1. And if we're getting a bit of a deluge here, 155. All right, bucket 0 overflowed. It overflowed in the bucket below that, which also overflows into the bucket below that. All right, we waited too long to call a plumber. Should have called a plumber a long time ago, or at least turn the water off so that our buckets don't keep overflowing each other. Yep, bucketing is right. It has the advantages of arrays, but significantly lacks flexibility. Bucket size of 3, same size table, same data. We can at least avoid some overflow here. And our indexes same as before, just additional column to add in, right? 7 equals 0, no collisions before. As we get our collisions, the buckets grow. All right, 41 comes along, and this time 155 comes along, and we didn't overflow our bucket at least. All right, so depending on how effective the collision resolution is, is going to drive how well our performance ends up being. Okay. Questions about collision resolution at the moment? All right. And concepts. All right, so some definitions here. Load factor. This is the percentage of how full the table is. Right. This is the factor, I should say factor. Ranging from 0.0 to 1.0. Where 0.0 is empty and 1.0 is full. Right, the higher the load factor, the greater the probability of a collision. Table size. Using prime numbers leads to a better distribution of values in the hash table due to the fact that we're applying a modulo operation on that data. And that's just how the math works. Don't ask me to explain the math. That's way beyond the level of math that I am comfortable having fun with. And so I'm going to demonstrate these two with .NET because we can peer into the underlying table and load factors that it's maintaining internally and see how the table sizes are going to grow. Now, we're very unlikely to see load factor of 1.0 for a hash table. And what we're doing is trading space for speed. We're intentionally going to waste space. We want there to be space because as new data comes along, if there isn't space, that's guaranteed collision, which means we have to deal with quite the problem. There are special circumstances, however. Circumstances where we can get there. one scenario where we can be there. Scenario is with perfect hashing. Perfect hash has no collisions in the table. Thus, our big O will actually be 1. It's the ideal operational complexity or asymptotic notation for our hash table. Ideally, is going to be big O1. So any generalized hash table with random data, we're going to expect collisions for a given sample set of data, and we'll be close to 1. Our average complexity will be 1 for non-trivial hash functions. Worst case, of course, still going to be linear, because if everyone wants to go play in the same bucket, whoever ended up in that sandlot last is going to be squeezing themselves in and having a hard time getting to a shovel. With a perfect hash, it's big O1 across the board. Best case, worst case, average case, because there are no collisions, because we have perfection there. Next step from a perfect hash is a minimal perfect hash, which is a perfect hash with a load factor of 1.0, right? Meaning we're not wasting any space, which is very difficult to do. To get to either of these situations, you're going to most likely need to know what the data is ahead of time so that you can specifically tune the hash function and or table sizes for either of these. For perfect hash, right, you might just be able to tweak table size and get things to flatten out and be completely normalized or distributed rather. With a minimal perfect hash, well, you have to know how many keys there are because the tables have to be that big. So for example, all right, let's look at a scenario where we can try and get this. C++ keywords. How many are we at these days? A handful. Let's get a quick count. We've got 97 lines here. So we have 97 keywords in the C++ language. All right, so one of the jobs of the compiler is to lexicographically break apart your code. And every time it finds a keyword, it has to look up what is the grammar for that keyword. If I see an if, right, then we're very helpful there, right? So if is going to expect one of these grammars to be present. So we see, we read the code, run an if keyword, look up the grammar for the keyword, and then as we start processing data that follows that, we're checking that the code that follows is adhering to the grammar of the C++ language. Right? Looking up keywords and their corresponding grammar is something that's going to happen quite often. Right? It's most likely that the compiler basically has it hard-coded. Maybe it's a switch. Yeah, I don't know how much faster it would be to hard-code it with a switch as it would be to actually build the dictionary and then use the dictionary, because dictionary is close to constant time, 97 keywords, so a 97 branched switch statement. That's a lot of branches. So that's a lot of equality testing. So it's kind of behaving like a linear search. Effectively with if or else if or branching with switch statements. So having a dictionary should perform better. And since we know the keywords of the language does not change often, we can spend the extra effort to say, IDE ABC can compile a 1 million line C++ application in 2 minutes. Our competitor compiles it in 7, right? It's a selling point to that IDE that they can compile the source code faster because they've optimized the things that the compiler needs to do to take a code file and transform that to the corresponding binary, right? So, and to optimize an application, you want to look at what are we doing a lot? What, right? If we're doing 10 billion things a day in this application, and we see that we're doing this one thing 1 billion times in a day, and that's normal for any given day, we want to analyze it and seek out what we can do to make it more efficient. Because if we can cut the amount of time that takes that, we can reduce either the costs to doing those operations, or it can be a selling point to the product that it is much faster than the competitor, or that speed might be so critical as that it's just strictly necessary. I think I probably mentioned this way back on the first day. Several of the things that we talk about in this class, right? We talk about the O notation is if we're talking about real-time systems, right, every fraction of time is potentially critical and have real world consequences. Right? Even if we just say in the world of business, right? Communication of information from Europe to the New York Stock Exchange, right? There's several fiber optic cables between like London and other places and New York. And people pay a significant premium to have systems that go onto those fiber networks right at where they come out of the ocean to get information faster than their competitors, because if they can make their trade 10 milliseconds before their competitor at price A, knowing it's going to go up or down based on the information, there's all kinds of money to be made. So I have no idea how much they pay for that, but it's of significant impact. It's one of the things that the Starlink network is going to try to do as well. I've read some case studies where they talked about possibly installing another, a fiber line between New York and another place in Europe where the information becomes made available, looking at how many hundreds of millions of dollars it would do that versus the time savings, and that time savings on that network latency and how that would translate into actual money. Right? So time is not always critical, right? If you're playing checkers on a desktop application, the slowest component in that system, even with a horrifically written application, right? Someone in high school writing, oh, I learned how to write VB and they wrote a checkers program with teaching themselves sort of thing. It was probably going to be fast enough because the user is going to be the slow thing. The user's not going to notice 100 milliseconds versus 120 milliseconds type thing in that little checkers application, but an extra 20 milliseconds network communication for any real-time system, and that's a whole different ball of wax. All right, let's see. So it's going to be very rare to get a minimal perfect hash, but that's certainly something that can be achieved. But you have to basically align the stars yourself to make it happen. Let's see. Load factor table size, right? So resizing a table. Okay, resizing a table. The table needs to grow because we've exceeded capacity or allowed load factor. An entirely new table must be built as the size of the table will ultimately drive where in the table the values want to be. All right, so resizing a table would be a little expensive. We'll play with that later. But yeah, you have to rebuild the whole table. So that's why it's good to know when you work in the framework, if you know how much data or roughly how much data you're going to have with any dynamically sized table, like using the vector class, I assume they have a constructor that allows initial capacity to be fed to it. Especially I know in .NET, there are a number of container types that allow you to specify the size ahead of time, because dynamically growing a table is built-in capability that those types have, but growing a structure tends to be the expensive thing, and especially growing a hash table be one of those. Deleting, which we will do as a separate thing later, the hash table. Also need to be careful here. Careful here such that we don't break the lookup. Right, so the basic behavior of the lookup is to go until you find an empty cell. You reach an empty cell or finding the matching key. Finding the matching key, then we conclude the key is not in the data set. All right, so load factor needs to be enough that we keep the probability of collisions to a minimal set such that performance is good. Table size to try to keep things nice and spread out. And then perfect hashing. All right, perfect hashing will definitely make sure you spend some time reading on that. Need to dig up links, lots of links, plenty of reading to do here. But that's about it for the moment. Let's see. Yeah, so we still have the practice test to go over and the labs to talk about. So let's go ahead and take another 5-minute break. Well, that's what makes it dynamic, allowing it to resize. So the built-in question is, would you say the built-in dynamic hash table is not dynamic underneath the hood because of resizing? But no, it is dynamic because a dynamic data structure allows itself to grow. Right? Dynamic mean not static, because you have static binding, you have dynamic binding. And something that's static it's fixed in size. All right, we're going to take a look at in the file section, hashing folder, hashing.cpp. All right, main method does very little, creates a hash table and just inserts a bunch of data with our insert function. We have a few functions in here. The hash table is just an array. Right, so these are, it's more of a hash map than a hash table. Constructor, just make sure that the data in the array is something meaningful, and meaningful is going to be -1 for us to indicate that that particular location in the array is unoccupied by data. We have our insert function. It's going to take the data, apply the modulo hash function, right, which is also normalizing, right? So the hash function is using is just the normalization process. If that particular location in the table is empty, go ahead and put the data that we're adding to the table at that same location. If there is a collision, we're going to go ahead and tell it to go ahead and probe with that data until we find resolution of that, or the table's full and then we get back out here. So we're just going to do a linear probe. We're going to go ahead and get the starting position, right, the collision point, by applying the hash function again here. The code's not particularly efficient because it keeps reapplying the same hash function to the same data point multiple times. And then our first probe will just be 1 bigger. And the key thing here is we need to make sure we normalize the result so that it wraps around. This is what is going to make the array circular. All right, so this modulo makes the array circular. So if this table is 17 in size and our first indexing operation goes to index 16, 16 plus 1, 17, modulo 17 brings us right back down to 0. So 16 and 0 are not equal to each other. If the first location that we tried our collision resolution to is empty, drop it in, and we're done. Turn true. Otherwise, go ahead and increment, and we are going to prefix increments so that we make sure the increment happens first, and then modulo by the size, and we keep looping. So in the loop, looking for empty, going up by 1. Keep looping, looking for empty until we either find an empty position or the loop stops because the table's full and we failed to add the value, table's full. Yeah, that's our basic hash tables. Go to our online compiler, run it, spit out all this good stuff. All right, 10 went to 10, 20 went to 3. All right, just using modulo. We got a collision. Got a collision, insert. All right, so we had pretty good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 values out of 14 that didn't have any collisions at all. But you know, it gets to a point where the table's full. And attempting to insert any additional data at that point, of course, it's just still table full. All right. Seems I kicked this one too far up. It's fine. Hash table lab. It's going to be very similar to the code we just looked at, but that and a little bit more. All right, table size 27. We'll need a function called hash. It's still just using the modulo function. All right, takes an integer, returns an add function like I before, calls the hash function, and does linear probing if needed. And then the other half of the equation, we need a lookup function. Look to see if the value is in the table. If it's not, we'll return -1. And then we need a main that allows the user to add lookup items in the table. All right, so right, a menu. Right, so when we're saying user, we have to give the user the opportunity to do A, B, C, X, Y, Z, whatever sort of thing. You can add data and look up data. Right, add 10, look up 10. Look up 20, it's not there. Add 20, look up 20. There it is. Hey. Questions about the lab? And when I adjust the data out, I managed to adjust it a week further than we needed to, but so you have lots of time for this one. Not due till next week. We'll be adding some exercises to this one to modify this lab and change the hash function, change the collision resolution patterns. I just need to put a note somewhere so I remember to do that. Otherwise, we'll just go ahead and go over the practice test before we roll into our lab time for tonight. Any questions about any of the hashing stuff before we do that? Collision resolution using linked list. It's big O N, yeah, because everything might end up in the same list. Yeah, so if everyone collides in the same list, the last value will require looking at every element in that list, which is every element in the table. And if you're looking at every element, you're linear. Okay, let's see, where's the practice test? Oh, I've got the practice test slated for next week. All right, test 4 graphs. Okay, so you probably haven't looked at the practice test yet, so we won't go over it yet. We'll just make sure I can get it to open. Right. Let me make sure that link is working. Didn't remember to do that earlier. All right, so there's images for answers. Okay, that's working, so that's good. Okay. Right, so we have our representations, the adjacency list, and adjacency matrix, right? So I might give you questions that are the matrix, or you might need to populate the matrix based off of a drawing. Same thing with the list, right? I might give you the list, and you might need to populate what's missing, or indicates what's missing, what's wrong, sort of thing. And then from either of those representations, right, various algorithms might be applied to them, right? So it's entirely possible I could give you, right, find the minimum spanning tree using Kruskal's algorithm and not give you the picture, but just give you the matrix or the list, right? Because it's the same information, it's just a different presentation of that information. We have Right, all the types, right? Symbol graphs, directed. If there's any arrowheads, it becomes a directed graph. Right, multiple edges for multigraph, pseudograph, loops, etc. Then we have shapes, right? So don't confuse the types with the shapes. Shapes are basically the degree pattern of the vertices. Right, star has a degree pattern of 1 for every vertex except for that one central point. Cycle has a degree vertex for every one of 2. Wheel is 3 with the exception of the center point, which could be non-3. Complete graph, right? It's b-1 bipartite. This one, right? You basically just apply it, label these, see like test if this graph is bipartite, right? So that's A is in one set. These two have to be in the other set. This one goes in that set. We're so good so far, but we almost had it. This one edge here stopped us from being bipartite. We remove this one edge here. This graph could have actually been bipartite, where we could have just redrawn it. All right, do what I'm talking about here. All right, so let's label E and F, right? So we had 2 sets, A and B. Vertex A, B, and D, right? There's no edge between B and D, so that's good. There's no edge between A and C, so it's good. Then F came along, right? So can't connect with C, and E can't connect with C. So that was good, but then these two fell apart because of that one edge. Complete bipartite, right? It's just a little bit more extreme, except now we have to force all the edges. And Floyd Warshall, right? That's just our V cubed. That one wouldn't be the entirety of the algorithm because that just takes too long. And most would be one pass from a point in the algorithm. So I could say if we have a 5 vertex graph, say using vertex C as the jump vertex, for example, update the matrix. What's the updated values in the matrix for like a row or something like that? Right, we've got our searches. We've got Hamilton and Euler. Should pretty much be it. All right, the coding that could be on test 4 will be all about the adjacency list, adjacency matrix. Right, multidimensional arrays and our array of linked lists. The algorithms will just stay as algorithms. We'll just do the work product of the algorithms, not worry about the code for the algorithms. Any questions?
Quick question. Did you say that there's going to be coding on the test?
Yeah, any code for the graphs will be adjacency list and adjacency matrix.
Okay, got it. Thank you.
All right, that brings us to our lab time. There's no additional lecture for tonight. Hang around, help you with your lab, or answer the questions, or whatever may be. Otherwise, I'll see you next time. We're on Discord. Don't forget, Discord's still there. It's been quiet for a little while here. It's like spring break threw us off our routine. Have a good night.